This information is brought to you by Charles Sturt University.
Morning again, guys. So, what we were looking at yesterday was looking at the idea of a graph, which is maybe best thought of as being a network. And so we were looking at adjacency matrices. So let's have a look. So we had graphs, and we were trying to work out a matrix, which is a rectangle or square in this case of numbers, which just represents the number of edges between each of the vertices. And so I just had a little digression towards the end of dealing with these matrices, so being able to add them, which is straightforward, and then being able to multiply them. So that was the very last thing. So just a cut off at the end there. So just for the people who missed the recording, we multiply these two matrices. We'll do some more today to get that sort of answer. So that's what we're up to yesterday. So now we've got some things on matrices. I want to apply some of those ideas of dealing with matrices back to the graphs again. So this was one of the graphs we looked at yesterday down the bottom, and this is the corresponding adjacency matrix. That's right. So that's the corresponding adjacency matrix. So I want to do a few things with it. So first of all, I want to work out what m squared is. So let's just take a snapshot. So to work out a square of a matrix, you just do the same thing for numbers. That means you just multiply it by itself. So m squared would just be multiplying by itself. So first of all, let's just do some calculations, and then once we've got it in front of us, we maybe think about what does it correspond to. So we'll just set the picture of the graph so we have that in so we can see it. So that's our graph at the top, just to think what we're having. We've got with the vertices A, B, C, and I always think what the other ones are. D, E. So that's the labelling of the vertices. So what we're going to do is multiply the two matrices together. As I said, the best way of multiplying matrices together is to set them so the first one is sort of down the bottom, and the one's rising above it, and then the answer will sit right there in the gap we leave between. And when multiplying square matrices like we've got here, then the resulting size will be the same. You can get other things happening for rectangles, but that's another day. So we'll have a square of answers. So see, we've got 25. This is 5 by 5, so we'll have 25 different numbers to work out. And you have to work out each in turn. So I'll do a few. I'll let you do the rest of them. So for the top one here, you want to go along the row and down the column that match that particular number. So you want to do that. You need to do it 25 times. So each time, you multiply the matching numbers up. So you're going, I've got 0 times by 0. Then so I'll write the whole thing. So 0 times by 0. Next one is 0 times by 0. Just do lots of different products. Next one is 1 times by 1. Next one is 0 times by 0. The last one is 1 times by 1. And then you get all these products, there's 5 in this case, and add them all up. What do you get in this case? 2. That's our first number. And then you want to repeat that same idea for the other 24 numbers. So let's do another one together. This one here would be going along this row down the column. So it'd be 0 times by 0, so nothing. 0 times by 0, so again still nothing. 1 by 1, gives you 1 finally. 0 by 0, nothing more. and 1 and 0 gives you nothing more. So if you add them all up, you get 1. And then you need to keep going. Do you want to how about you go do some more yourself? So you guys need more practice than anyone else. I've done a few in my life. So I'll pick one more. Let's just start writing down the rest of the grid. So you pick this number here, for example. To work at any other number, you want to go down a row, so along a row, down a column, multiplying matching numbers up. So it'll be 0, 0, 1, 1, 0, 0, 0, 0, 0. So the only time you'd ever get something would be just from multiplying these two ones together. Everything else would be just lots of zeros giving you. So it'd be 0 times by 0, plus 1 times by 1, plus 0 times by 0, 0 times 0, 0, 0. There's much left. So have a go, see what you can get, and then I'll talk more depending how you go. So if no one's getting it, I'll explain further. But if everyone gets it quickly, then I'll go, okay, that's good. But it's good to see what you're actually going to know and explain accordingly. And if you've done it really quickly, the next question is, what does it mean? So it's all based on this graph at the top here. So it's all something to do with that picture up here.
What does it mean?
What does it mean?
Multiplication. What does anything mean? Oh, it doesn't matter. You can use it.
Let's keep it a bit more constrained than what does anything mean.
It's a number. It would be a third one instead. Yeah, okay, 1. 0, 0.
Just unravel off the rest of the front row, just the top row there, just to give it. See if it's coming off right.
It's fairly straightforward, and then you can use the second row. 1 and down there now.
1.
0, 1.
Yeah, 1, 0, 1. It's just the first row, just to keep on track. It's not a test, so you can talk to each other, it's okay.
Calculator.
Right on the bottom for huge free for you. See if we can finish it off. So with matrices, there's lots of mini calculations. So the arithmetic is not difficult.
Yeah.
The first problem is trying to understand what we're doing here, and it doesn't seem very intuitive at all what we're trying to do is combine these two things together. But once you get over that, the other issue with matrices is there's so much arithmetic it's easy to make one little mistake, one somewhere around. So although each individual thing is not difficult, it's just that you have to do lots of it. You think about it, you're doing lots of different products there. So, someone will rattle off what the rest of the entries are.
12001, 10311,
1, 0, 3. You say 1, 1. Yeah. So, who would like me to explain to them? Let's just do one more. Just do this 3. That's the one that stands out as the thing, but a little bit different. So to work out this one here, you have to go along a row, down a column. It's always the matching row, matching column. And if you write it as I've suggested, it's really easy to see what the matching row, matching column is. And so you're just getting the corresponding numbers, so the first 2 numbers, multiply them together. Next matching numbers, multiply them together. Next matching numbers, next ones, next one. So it's always just matching numbers, multiplying each of them. So you're getting, as you can see, 5 products in this case. For each of those, just add them up. So you 1 plus 1 plus 0 plus 0 plus 1. So it gives you the 3, which is, thanks Jacob for saying that. So, and that's the basic idea all the time. So along a row, down a column, multiply matching numbers, adding them all up. So this resulting matrix down the bottom here is m squared, where the first one here is m. So let's give some names to them, try to think of what they mean. So m here is the adjacency matrix. So adjacency matrix is basically the number of edges that connect vertices to vertices. So for example, this one here says there is one edge from the first to the third vertex, essentially. And this one here would say there's one edge from the first vertex to the 5th vertex. So it just matches up the picture. So that's what the adjacency matrix is, just the edges, essentially. What does m squared correspond to? Essentially, m squared is you're basically taking one edge. That's what the first m is. The second image, you're taking another image. So it's really all paths which contain 2 edges. Or all paths of length 2 to keep it short. So let's just look at the 3 here. So that would correspond to the third, so that's the third row. That corresponds to paths starting at the third vertex. So starting here at C. And they would be in the third column, so paths ending at C. So, how many different paths are there starting at C, ending at C, which are of length 2? Well, the answer is, the matrix says there's 3. Let's see if we can see the 3 in the picture. So the first of them would go to A and then back again. And that corresponds to that term. That corresponds to that term in our product. The other option would be to go from C to B and then back again. That would correspond to that term. And the last one would be C to E and back again. It would correspond to that term. And you can see there's no way to go to C to D and back because it's not possible. You can't just do loops forever at C because there is no loops available. So there are 3 different paths of length 2 from C to C. Picking another number. So we pick this one over here. That number would say we're starting in the first row. That means the first vertex. And we're finishing in the 5th column. That means we're trying to finish in that 5th vertex, so from A to E essentially. So we're looking at 1 says there's one path of length 2 from A to E. You know what the path would be? And A and back end would be A to A. So when we start at A, go somewhere else, and then back and finish at E. What's the middle position?
A to C, E.
Yep. A to C to E would be the only path of length 2 from A to E. That's the only way you're doing it. And that's what this m squared tells you exactly how many different paths are there of length 2. So m squared corresponds to paths of length 2. So length, and the length of a path is just how many edges you have to visit. So the adjacency matrix then really is the paths of length 1. There's another way of thinking about it. What do you reckon m cubed would correspond to? Yeah, so m cubed would be paths of length 3. So, and you can do higher ones as well if you wanted to. So, let's just remember that. Let's do one more thing. Let's do m squared plus m. Let's try to do this mathematical operation for the moment and then try to think what it corresponds to in the graph. So m squared is what we worked out a second ago. That's m squared. M is our other matrix. So these are two different matrices, and I want to add them. So they have a quite significant, they mean something in the graph, but let's just look at it just mathematically for the moment. How do you add matrices together?
Row by row.
And the answer is term by term even. So you really just add, this is much easier. You don't have to combine lots of things together. You really just add one term at a time. So you've got 25 numbers, and each of them just match up the numbers and add them up. So this first entry here would be the 2 plus the 0, which is 2. And the next one would be 1 plus 0, which gives you 1. So this one's much more straightforward, fortunately. So rattle off the rest of the numbers for me. 2, this is 1 plus 1. Hope you can do that one. Next one.
0, 2, 1, 2, 1, 1, 1, 2, 1, 3, 1, 2, 0, 1, 1, 1, 0, 2, 1, 2, 0, 2.
Okay, now there's no point just copying it down, which you could do, I guess, but you have to understand where all the numbers come from. So can everyone understand where Corey rattled all those numbers off? Thanks very much, by the way. So addition's easier, which is nice. What does it correspond to? So what is m squared? M squared is the number of paths of length 2 from a vertex to a vertex. M is the number of paths of length 1. What do you reckon the sum of those would be? What does plus correspond to when we're doing counting sort of things?
Or.
What's an or, really? That's right. So this would be paths, length, well, 2 or 1. So the or and the plus really match up to each other. So there's a number of paths of length 2 or 1. So this is the number of ways of going from one place to another by 1 or 2. And you could do heaps as well. So you could go, well, you could do m plus m squared plus m cubed plus m4, etc. If you want to do that, would be the number of paths going from, it's a number of paths of length 1, 2, 3, or up to whatever number you wanted to do, connect the graph. And if you keep doing those higher powers, if you're always getting zeros present, that means that you're never going to be able to connect two of the vertices together. Which seems like a long way of proving that it's disconnected, essentially. Now, there are tricks with doing powers of matrices, which I'm not going to explain today. It requires more theory, but you'll do some of that sort of stuff in, say, Maths 101 if you guys do that subject. So there are certainly useful ways of looking at powers of matrices, and doing a sum of matrices like that, again, there are tricks for it. Like, it's a geometric series, but of matrices rather than of real numbers. There are lots more mathematics there behind it all, but we'll just look at the application. So there are though it seem like daunting lots of calculations, it is useful to do some of these sort of things. So you can use the matrices to accurately calculate number of paths of various lengths that you want. So, just some questions to get to think through the adjacency matrix. How can you tell from the adjacency matrix if the graph is simple? So you have to remember what the definition of simple means. What does simple mean again?
If there's one thing connecting all the things.
Okay.
If there's no twos on the adjacency graph, then it's simple.
Okay, so simple requires two things. The first of them is that between two vertices you'll have at most one edge, which, as you said, that means you can't, the highest, any in the adjacency matrix, the highest you never get is a 1. There's a second thing about being simple, and that is you can't have any loops on a single vertex. So you can't have a loop.
Two different ways. That would create a 2 if you had a loop.
Yeah, okay, so that would create 2. So it really requires that on the diagonal, that really forces everything to be 0 on the diagonal. And so diagonal in matrix always means top left to bottom right. So we don't have diagonals the other way, so just top left to bottom right, and that would have to be 0s for simple matrix. But you're right, I mean, what you said was correct. What would the adjacency matrix look like for a complete graph? What does complete mean?
They're all connected to each other.
Okay.
Being the same number of, like, it'd correspond to the number of vertices, wouldn't it? Times 2.
Well, it depends.
So what's an example of a complete matrix? So we did one yesterday. So you got all these dots. Every possible edge is connected. That's what a complete graph looks like. What would its adjacency matrix look like? Well, the first vertex is not connected to itself, so it's simple. So because it's simple, you're getting 0s down the diagonal. So it's still a simple graph. With vertex A here, the first one, how many times is it connected to each of the other vertices?
1.
Once each. So therefore, we're getting 1 across that row.
1 everywhere.
So pretty much it's 1 everywhere else. So a complete graph would have 0s down the diagonal and 1s everywhere else. And you could explore, if you wanted to, what powers of that would be equal to. And there's lots of symmetry, so the diagonal will always be the same, won't be 0, and the off-diagonal entries will always be the same, but again, not necessarily 1. So you can explore that if you wanted to. So just reminding you of the definition. So simple means not multiple, so you're going to have at most one edge between two vertices, and you can't have loops. And complete means a simple graph where all possible edges are included. So basically, where we're looking at adjacency matrices from is how do you represent a graph in your computer, really? So graphs are useful data structures. How do you represent it in the computer? And so one way is to represent it using an adjacency matrix. That requires you to have a big grid in your computer. Now, if most of the entries in the matrix are 0, you're probably wasting your space. And so you can try to represent it in other sorts of ways. So one simple trick, if it's an undirected graph, it's symmetric, so the top half of the matrix and the bottom half will sort of match each other. So a simple trick is to only store half the data, not all of it. And that requires a bit more fiddly work in terms of coding up where to extract entries from. But you could take the time to do that if you want to save space. So that saves half the space already. But if other cases, well, if there's still lots of 0s, that's still wasting space for you. So here's the other ways of representing it. And these sort of stuff is explored more in another subject that you guys might do called data structures, ITC 322. So just mentioning some of this and foreshadowing some of the things you might do in that subject. So one is called an adjacency list. And again, this is mostly used when there's not that many edges around, and you don't want to have to write a whole row of the matrix with mostly zeros and occasionally a 1 or 2 there or whatever it might be. And so basically you first choose your vertices, work out a numbering for them, so just 1, 2, 3, etc. Then you'd write, so the basic sort of format is you write down the first column would correspond to all your vertices, and you have to have numbered for them. For each vertex you then produce a list of all the vertices that are adjacent to it. What does adjacent mean again?
It's got at least one vertex connecting it.
Okay, it means it has an edge. It means it has an edge connecting it. Yes. So 2 vertices are adjacent if there's an edge connecting it. So we just basically got a list of lists, or something like that. And again, you can make them arrays, etc. If you like it. Leave that. So that's the basic idea. Let's try to work out the adjacency list for this particular graph. Now we just the one we've just been working with, so that's the adjacency matrix, which had lots of zeros in it, and just trying to show the adjacent list looks a bit more compact is the intention. So again, we've got to number the vertices. That's the first thing you have to do. So you have the vertices, vertex, so 1, 2, 3, 4, 5. And then you write down all the vertices adjacent. So for the first vertex, 1, yep.
I'm sorry, Michael, but are you aware you're spelling adjacency wrong?
How do you spell it?
There's no N before the first C. It's not adjacency, it's adjacency.
Thank you.
You've been doing it repeatedly and it's finally just gotten too much for me. Sorry.
No, that's all right. The C back in there.
Don't bully him.
No, it's fine.
The one on the right still isn't fixed though.
Quick
pointers. Much better.
Okay, so for vertex 1, what are the vertices that are adjacent to it? Which are the vertices which have connected by an edge to vertex 1?
5.
So 3 and 5. What about number 2?
3 and 4.
3 and 4.
1, 2, and 5.
So for number 3 is 2, 3, 5. 4, 2.
1, 2, and 5, not 2, 3, and 5.
Yep. And the last one?
1 and 3.
1 and 3. It's useful to have them ordered, so because you're often trying to troll through these lists to work out if an edge is present or not. And so if you've got them ordered, and you go, I want to know if vertex 1 is connected to vertex 2, and the first thing you come across is 3, okay, I know automatically I can exit the loop. So it's useful to have them in order, just to save the time when actually trying to run the algorithm. So that's what the adjacency list looks like. So if there's lots of zeros, then you can make these less memory and quicker to run than the adjacency matrix approach. In this case, it was a 5 by 5 matrix. 25 numbers doesn't take that much space in a computer. It really wouldn't make much difference with this small stuff. But if you've got a rather large matrix, sometimes these tricks are important to do. Yeah, like that Facebook stuff. Suppose you added one more edge. Let's suppose you just put one more edge in, so an edge joining 1 and 4. What would that do to the adjacency lists?
You change the 1 and the 4.
Okay, so you'd have to basically add a 4 in the adjacency list for number 1. You'd have to have a 1 in the adjacency list for number 4. That's pretty much it.
Now you've got a fish. Yeah, you do have a fish.
I guess.
During the exam, it's like, what does this graph look like? Gonna nail this exam.
Okay. So, so the problem with adjacency list, it still shows every single edge twice in there. And so, and again it has a list of lists, etc. And so sometimes all the overhead of having a list of lists gets much when it's really, really sparse. So another option is just have a list just of the edges by itself. So stripping it down, so it takes up less space. The downside to this approach is it really just has all the lists, it's really just a list of edges. And so if you want to check for edges, sometimes you have to troll through the whole list. So it can be actually a bit slower using it. But it's really only convenient for very sparse stuff. And so sparse means you don't have that many edges present relative to the number of vertices. So it's a linked list. So do you guys know about linked lists? In other sense?
I have seen them.
So what's a linked list? You don't have to know, I'm just curious what you do know, that's all. So a linked list data structure in general terms is you've got an element which contains your data, so it's going to be an edge in this case, and it has a pointer to the next element in the list. That's a singly linked list. A doubly linked list would be a link to the next element and the previous element. That's a doubly linked list, for example. So we're just going to we'll just make it simple. Has anyone heard of these things before? One person might look good. Has anyone heard of a singly linked list before? No? Okay. So some of these data structures are coded up in, Java would have them, for example. That's not the only implementation of lists I have, but that's one way of doing it. So I'll explain in a second. So what I'm going to have is in the memory in the computer, there'll be a bunch of addresses. Each of these addresses would be the corresponding cell that we want to have in the list. Essentially what each cell contains is the information for the edge we want in itself, plus a pointer to the next element of the list. So let's just try to have a look. So what we're going to do is we're just going to go through our matrix and just write down a bunch of edges. So the first thing we're going to do is we're going to add something at address 1. So let's just pick a random edge. So what's one of the edges we can see here? We'll make myself all
1 to 3.
Okay. So pick 1 to 3. It's a convenient place to start. To begin with, that's the only thing in the list. So we need to tell the computer when we're going to search through it that's the end. So it's convenient to say there is nothing next. So it has a null pointer, so to speak, at the end. So 0 is just a null pointer. So we start. So it's basically just one element in the S. The 0 just says that's the end of it. Then we want to add another one. So let's do, say, 3 to 5 this time. So when we add another element, we need to say that the first element has something else after it now. So the thing after it would be not 2, would be the element at address 2. Yeah, so circular references wouldn't go very well. And the second element would be after that. Well, nothing, so a null pointer. So in C, or C++, you actually do use 0 for the null pointers. In Java, it has a construct to stop you doing some stupid things, essentially. You may have seen.
Yes.
So let's add one more. So another edge we want to put in is, say, 1 to 5. Now you think, oh, just chuck it on the end. It's useful to have the edges sorted in some regard. So a useful way of, so the natural order for putting the edges is basically for each edge you write down the vertices in numerical order. So you do. So I got 1, 5. I won't write down 5, 1. I'll write down 1, 5. Just make it natural ordering. And another actual ordering would be basically to order those naturally. So that would be do everything from vertex 1 first, and then do everything from vertex 2 next, and then everything from vertex 3 next, etc. So the natural ordering would put 1, 3 here. That would really be the first entry. And then 1, 5 should be the second, and this should be the third if it's more the natural ordering. So when I want to add my 1, 5 in here, I really want to add it between these two different entries. So how you do that is to say, look, I really want to add 1, 5 just after the 1, 3. So I'm going to change the address here to 3. And then what address should I put over here? 2. So that's just basically go along the list, breaking it open, chucking something in between effectively. Change the links on either side to insert it. What's one more we haven't done yet? So 2, 4. Here's one more edge we can add. So again, we want to work out whereabouts in the list we want to do. So we start here, go to 3, that's still too small. So you go, I want to insert it after this element, I want to add it after that edge. So I'm going to break it open by deleting that. That one now needs to point to the next one I'm just adding in. And 4 now needs to point to 2. And then you can go on from that. Now, when you're utilising this data structure, you don't really care about where the cells are located in memory. Of course, you just got to go, what's the edge, what's the next one, and it just tells you where it is, essentially. You don't have to really think about where it's really stored, but in memory, that's what it looks like, essentially. And therefore, you don't have to worry about having it pre-sorted already, you're just sorting as you're going along, effectively. So this is really very convenient in terms of space storage. It doesn't use much, but you can see it's going to be a bit of a pain to utilise, because to know if any edge exists, you're going to have to search through it. At least if it's sorted in some sort of way, like this natural ordering, you can at least go, look, I've got to a point where I should be looking finding the edge and it's not there, and so therefore it can't be there, therefore I can exit early. But still, if you're trying to look for the edge 4 to 5, for example, you have to search for the whole edge list just to find it's not really there in this case. So it's not necessarily the most efficient in terms of time, but it's a trade-off. So like lots of algorithms, you can make something faster by using more memory, and sometimes you can make things slower by using less memory. So you've got one or the other. So what do you want to, and again, some sort of trade-off you want to do there. And if you're using lots of memory, as you may learn data structures, that means you might have to be using long-term storage, which is slower anyhow. And so you've got how do you, and you're choosing the right data structure for the right sort of memory storage is important as well. But you'll do more of that, as I said. We'll touch on a bit more data structures a bit more in the subject, but only little bits. You do a lot more in the subject called data structures, naturally enough. And things like graphs and trees are really useful ways of storing information. So just a few quick things on directed graphs, or digraphs for short. We'll do some exercises on these later, so either on the online meetings for distance students or you guys in the tutorial. So a directed graph is a graph where every edge has a direction. An example of this, of a directed graph, sometimes it's called, so it has lots of the same lingo as before, so it applies to directed graphs. They've just got directions, that's it. There's a few special terms, which I'll mention some. An example of this is called a directed acyclic graph, which are called DAGs for short. Not my acronyms. So they are used when you're doing scheduling. So things like Excel would use it. Any spreadsheet program would use them. When you type in Excel, the intention of Excel, you have lots of formulas in them, and a formula needs to. If you've got a cell involving a formula, it needs to calculate that based on a previous cell. And then that cell might have another calculation which requires other cells. So a directed acyclic graph in Excel would basically, all the cells with formulas in it would be the vertices. And an edge, a directed edge, would be, if that cell requires, the previous one would have an edge to it. And the direction goes which way the dependency is. And in Excel, you can actually ask for it to show them. You can just say, show me the dependencies of this cell, and it shows you all the arrows. So actually, you can actually quite visually see these directed acyclic graphs in Excel if you wanted to. If you've got a reasonably sized complex spreadsheet, there can be lots of arrows around. And for Excel to work properly, it has to be acyclic. What does acyclic mean?
No cycle.
No cycles. So no loops. Do you know what? If you try to it in Excel, try to have a cycle in Excel. Do you know what it calls it? I don't know how much Excel you know.
Just errors out.
It says an error. It's called a circular reference, and it complains to you, and it shows you what the circular reference is. So it detects them, and as soon as it detects them saying, throws an error and says, you better fix it, otherwise I'm not doing any calculations for you. So Excel really does work on a directed acyclic graph. So this idea of graphs, as you can see, and directed ones in this case, really underpin lots of common computer technologies you'll see. And also in project management, a digraph is really just a PERT chart, which I've never remembered what it stands for, project something or other, or Gantt charts, etc. So these are common ways of representing information. Like a normal graph, we have degrees. But unlike the graph we had before, we now have arrows on things, arrowheads. And so now when we're trying to count the number of edges at a vertex, we want to specify if the arrows are going out or if they're coming in. So when we just talk about the degree, so to speak, we want to talk about if it's going in or out. So we have in degree and out degree. So in degree is number of arrows coming in, or number of edges coming into a vertex. Out degree is number of vertices number of edges going out. And so we have similar sorts of results we have for degrees. So if you added up all the degrees for an undirected graph, you get twice the number of edges. Since we've got more precise information here, if you count the total number of in degrees for all vertices, or likewise count the number of out degrees, we get the number of edges. That's all it really is doing, is counting the number of edges. The same sort of idea, similar sort of result. You can do adjacency matrices. All the other data structures still apply for directed graphs like they did before. So adjacency matrix really does work for a directed. It's just that it won't be symmetric anymore. So the number of edges from A to B may not be the same number of edges from B to A anymore. So it may not be a symmetric matrix. But you can use lots of the same techniques. You still can work at number of paths, length 1, 2, 3, using the same idea of multiplying matrices. All that still applies. You can still work out things like Euler circuits and Euler paths. What's an Euler path again? We did it yesterday. Doesn't mean you remember it.
Along each line one time.
Okay, so an Euler path is going from one vertex to another, so you use every edge exactly once. That's what you're saying. And an Euler circuit is just starting the same, means you start and finish at the same vertex using every edge exactly once. So for a normal graph, the condition of if an Euler circuit or Euler path existed really was dependent upon just the degrees. Same sort of thing applies here. So you can traverse a digraph, or you can find an Euler path or Euler circuit, depending on some conditions. So pretty much, if for a circuit to be able to go all the way around, the in degree and out degree have to be equal at every single vertex, which makes sense, right? So if you're trying to go on every single edge, basically you're going to come into a vertex and going to leave it. So you've got to have a pairing of the in and out degree for it to really work. If you want a path, at the starting point, your in degree can be one more than the out degree, because it's just to start from. You go around a bit and you finish somewhere, and the finishing point can have one more out degree than in degree. And that's basically how you check it out. So this, I've just drawn a graph which has a very clear, to me at least, traversal. See, the traversal is just going 1, 2, 3, 4. That would be a traversal going all the way around the different edges. So, so this is got a cycle in it, so this is not acyclic, this is just a direct graph, cycle in it. How you can show that it's got a traversal is looking at the in and out degrees of everything. So let's call them A, B, C, D. Let's do the in degree and the out degree. So what's the in degree of A? So how many edges are pointing into A? None. Pointing into B? One. The C? D? Okay. And
There's two into B.
yep.
Don't worry, Corin, I can't count.
So there's 2 going to B. Thank you. What's the out degree? What's the out degree of A? How many arrows are going out of? 1. Out of B?
1.
That's 1 now. Yep. 1. 1. So if you do the difference between these two, so the I'll say out minus in, you're getting 1 minus 1, 0, 0 in this case. So for to get an Euler circuit happening, you'd have to have zeros across the board. So if you get zeros everywhere, so for the differences, that means you could have an Euler circuit would exist. And then with ad hoc, you can try to work out what it is. If all of them is zeros except for 2, that are not 0, one's a 1, one's a minus 1, like you can see here, then you have an Euler path. Where the 1 is, that tells you where you're starting from, that's your starting point, and where the minus 1 is, that's where your finishing point is. And otherwise you're going to do a transversal going along every single edge otherwise. That's how you check for Euler paths, Euler circuits, or another word for it is doing a transversal of the graph. So we'll finish it there. So what I want to look at next week is looking at trees, which is a special type of graph. And I've already mentioned it. They're pretty much acyclic connected graphs. But they're very useful data structures for me. So they're useful in their own right. And because they're strong conditions, they have lots of special properties, which make them easier to use. But we'll look at that next week. So I'll see you guys in tutorials.
I can't wait for that one.
What was the difference between the half